Great. All right, thank you so much again. So in this tutorial, we'll first look at the definition of explainability, since it is not very clear from the literature. Then I'll talk a bit about post-hoc explainability, in particular surrogates, and how we can make them modular, followed by surrogates for text, image, and tabular data, an in-depth dive into how to build them, how they work. Then I'll try to conclude all of these. We'll break for 5 or 10 minutes, and then we'll move on to the hands-on with a Colab notebook before closing this session. So what is explainability? If you look at the literature, there are some pieces that try to define it, but there is not universally accepted definition. Some people like Lipton define it as simulatability, which is the ability of a human observer to simulate a black box model. So if you basically want the human to replicate predictions or decisions of a model in order to deem the system explainable. There are counter-arguments to this proposition, and this is, for example, Saros' Chinese room theorem. And the idea behind the Chinese room theorem is that you close a person in a room, and this person does not speak Chinese whatsoever. But in that room, there are books that would allow you to translate a note in English into Chinese without actually understanding the language. So rules, dictionaries to transform English into Chinese. And you slip a note in English from one side of the room. The person uses all of these books to translate it into Chinese and slides it out at the other end of the room. And this means that the person can accomplish a task and is able to simulate a person speaking Chinese or being able to translate English to Chinese without actually any understanding whatsoever of the language, which is a stark contrast to defining explainability as pure simulatability. In addition to these two opposing definitions, there is also the concept of mental models. And in the literature, especially in the explainability literature in machine learning, you can find two types of mental models that are helpful when defining explainability. One is functional, which allows you to operationalize a certain concept without actually understanding it. And I'd like to give the example of a light switch. So for example, we all know that if we flip a light switch, the light bulb turns on. So if our task, if our goal is to get some light, we know that we can just flip this little switch and we'll get some light in the room. And this does not necessarily mean that we understand how it works on any level of depth. And then you have the structure model, which goes a bit deeper than just pure operationalization of the concept. And this is, for example, to a different depth understanding how electrical circuits work, or maybe even deeper into what physical phenomena underlie electricity. And this becomes then a structure model that is more generic, more general. You can apply it into other electrical circuits, not only the light switch. So these are two opposing mental models that kind of resemble the simulatability in terms of functional and structural and more in-depth understanding. There is a really good book by Roger Penrose back from late 80s called The Emperor's New Mind. And in this book, Roger Penrose explores this sort of concepts in terms of artificial intelligence. And as you can see more recently, these concepts have been rediscovered in explainability. But regardless of all of that, this doesn't really give you any precise definition. So before I dive into any sort of machine learning explainability, I'd like to define what I mean by explainability. And I define it as some background knowledge that a person comes with that is used later on in conjunction with transparency insights into a black box, be it a machine learning model or whatever else. And then you apply reasoning to these transparent insights, given your background knowledge, in order to get some sort of understanding of this process. And all of this constitutes explainability. And you may have noticed that there is a implied background knowledge here, which pretty much assumes that the explanation is targeted at somebody. So there is a person, an explainee, that should walk away with understanding. We are not producing explanation that go into the limbo. There is a target at whom we are trying to aim these explanations, these insights. So just to give you a more precise example of how it works, here to the left, you can see a few examples of exemplars, basically a sort of transparent insights into a machine learning model, which tell you the humidity, the temperature, and rain, whether it's raining or not, as features, and then the black box decision whether a person likes the weather or dislikes the weather. So this would be some transparent insights. Then we come in with our background knowledge with what all of this feature means, and we apply a reasoning. So here I'll do the reasoning as a human being, but we could also outsource this reasoning into a machine. So we could design another algorithm to do the reasoning for us. So in this case, the reasoning would be as follows. For the two examples of, well, for all of the three examples, like and dislike, the temperature and the rain do not differ. The only differentiating factor is the humidity. And then we can zoom in on the humidity and see that given the temperature being 23 degrees and the weather being sunny, the only differentiating factor is humidity. So if the humidity is low, the person likes the weather, whereas the humidity is high or medium, the person dislikes the weather. But the technical aspects of explainability is not all. There are also human-centered aspects that we should consider when generating explanations or designing any sort of explainability or explainable machine learning. And this has been largely forgotten until this paper by Tim Miller has been published, Explanation in Artificial Intelligence, Insights from the Social Sciences. And this paper is quite lengthy, but the two key takeaways for me are that explanations tend to be interactive dialogues as opposed to one-directional offloading of information onto the explainee. So it's more of a bidirectional conversation rather than just stating facts. And also humans tend to prefer contrastive statements. And you could have seen a contrastive statement in the previous slide where the explanation said, oh, had the humidity been low, then the person would have liked the weather better. So that should give you a summary of what explainability is all about in machine learning. And now let's move into something more precise. And these are surrogate explainers. So, but what do I mean by a surrogate explainer? Here we assume that we have a black box and we are trying to explain it. And we do so by building a simpler model, a more transparent model that approximates part of the black box or the entire black box in a way that allows human explainees to understand what's happening in there. And we can either have global surrogates, so we're trying to approximate the entire black box process, or we can have a local surrogate where we are just trying to approximate a small bit of the black box. So for example, imagine trying to explain either a whole predictive model or just the behavior of this black box model for a certain person or a group of people, like a cohort. Then we can also have two different types of surrogate in terms of what sort of information we use to construct them. We can have a structural surrogate, in which case we are building a surrogate based on the structure, on the mechanics of the underlying black box. And just to make it a bit more precise, imagine a huge wide and deep decision tree. And you want to, it's too big to comprehend in its entirety. So we are explaining just one small branch of it. And this can be achieved by, for example, cutting it out and then assuming that this is for a certain individual, applies to a certain individual, or applies to a certain group of people that we are interested in. This becomes our structural surrogate, just cutting out one branch of a decision tree that is precise, because we are basing it on the structure of the underlying model. Alternatively, if we do not have access to the underlying black box or it is too complex, we can have a behavioral surrogate. So then we just observe the behavior of our black box by feeding it new data points and observing the predictions. And we use these two pieces of information to build our surrogate. Then we plug our surrogate explainer on top of the black box. We generate explanations and we communicate them to humans. So this is the entire pipeline. Ideally, we would have another direction from the human into the surrogate explainer so that the human explainee can provide feedback and personalize the explanations. An example of a surrogate is LIME. You may have heard of local interpretable model agnostic explanations. And just to give you some intuition, some more precise intuition of how it works, the background here, the light blue and light pink, is our very complex black box decision surface. We are trying to explain the bold red cross, the plus symbol here. So we are fitting a simpler model locally to approximate the black box decision boundary here along this decision surface.
Hi, Kacper.
Yeah.
Sorry to interrupt.
Sure.
There's a question from Carl. I don't know if you can see it in the chat. Do we need to assume that there wasn't/isn't a glass box one as we start to try to explain the black box one? So maybe the question is, where does the glass box come from? Or maybe that isn't the question. Anyway, maybe Carl, do you want to ask the question? Let me just see if I can find Carl. Let me just, oh, here's Carl. Let's see if Carl, you should be able to talk now. Okay. But you have to unmute yourself. Okay, maybe that is not an option.
Right. I think the question is whether we can build a transparent model in the beginning so we don't have to explain it post hoc. And I'll get to that in a moment, if that's the question.
Okay. Okay. Yes. Carl says yes. Okay. No worries.
Okay. So like I said, here is a very simple example of a surrogate. And based on my explanation, you get some sort of intuition. This picture conveys some sort of intuition. And this is not necessarily always the correct intuition. And hopefully by the end of this talk, you will see why this picture, this understanding of LIME and of surrogate explainers in general may be misleading. So what are the benefits of surrogates? Why would we want to go with surrogate explainers? First of all, they are model agnostic. So they work with any black box, regardless of what sort of underlying process that you're trying to explain you can use surrogate explainers. They are post hoc, so you don't have to think about transparency up front. You can just install them at the very end and explain away your data points or your black box model. And finally, they are data universal, which means that they work with image, tabular, and text data. And that's because of interpretable data representations that I'll explain in a moment. The final property, universally with respect to data, means that regardless of what sort of data you use, you will have similarly looking explanations, which means that the explainee will not get confused, because regardless of what sort of black box you're explaining, you'll always get very similar looking explanations. There are some actual examples of surrogates, and these are LIME, which I showed you just a moment ago, also Uncurse and SHAP. There's also RuleFit, but RuleFit does not use interpretable representations, which means that you can only use it with tabular data. So based on all of this, it may seem like surrogates are a silver bullet. You just don't think about explainability whatsoever. You build your black box, optimize for accuracy or whatever your performance metric is. And then you install a surrogate at the end and explain the way, and everything is great. Well, it's not that simple. In computer science, we have this thing called the no free lunch theorem, and it pretty much stays in the context of explainability that no single explainer can be better across the entire spectrum of explainability problems. So even though you could possibly use surrogate explainers with any sort of black boxiness that you may come across in machine learning, they will not always give you the best possible result or even the correct explanation. And there are reports of that, of post-hoc explainers such as surrogates having poor fidelity. And what it means, what fidelity means, is that your black box behaves differently. Well, your explainer behaves differently in the region of interest to the underlying black box, which means that you don't quite mimic the black box well. Therefore, any explanation that you extract from your surrogate may be incorrect or misleading. And Cynthia Rudin has argued that instead of using post hoc explainability, we should focus more on building transparent machine learning models upfront. And to this end, we should try to find an XAI, explainable artificial intelligence process that could guide us and help us to achieve that, similar to what we have in data mining, like KDD, CRISP-DM, or big data processes that guide you through building and maintaining your predictive models. So as opposed to spending more time on building these surrogates and deploying them, maybe engineers should spend more time on actually building informative features and inherently transparent models. And explainability should not be an afterthought, just an afterthought. But then it requires effort to do these things. Whereas with surrogates, you can just plug them at the end of your machine learning pipeline and get some sort of explanations. So coming back to the explainable AI process, at the moment, building a generic process is beyond our reach. We are still very early in XAI research, but there were a few attempts. So one is ours, where we proposed an Xai taxonomy, a fact sheets that allow you to describe your explainer from both social and technical perspectives, and another more technical that allows you to abstract away some of the technicalities involved with machine learning explainers. Our taxonomy spans 5 different dimensions: functional, operational, usability, safety, and validation. And these give you some sort of framework for reasoning about explainers, describing them, or trying to understand what's missing or what can go wrong. Whereas the other one is, like I said, a fairly technical step-by-step development of black box explainers, but not necessarily covering all of the techniques available. So this is where our research comes in. We said, well, if we can't really develop an XAI process for the entire field, maybe we can do it just for a small bit. And we looked at what is the most popular part of explainability. And at the time, these were surrogate explainers, post-hoc explainability. And we said, let's try and create a process for building faithful surrogate explainers. We call our method BLIME, which stands for Build Lime Yourself. And it's a collection of tools, like a framework for building surrogate explainers, a meta algorithm that helps you to operationalize them, and also some analysis of different building blocks that constitute surrogate explainers, and some practical recommendations for putting all of this together. So this means that we can use BLIME to build flexible, faithful, possibly interactive surrogates, but it again requires effort. So it's not us, it's not a one-stop shop. It's not one tool that solves all of your problems. You actually have to put some effort to build a good surrogate explainer, similar to the argument by Cynthia Rudin, where she says, well, maybe instead of doing whatever you're doing, you should focus more upfront on transparency and make sure that your model is a glass box and you don't need any post hoc explainability, which may be misleading. BLIME constitutes of 3 main building blocks, and these are data sampling, interpretable representation, and explanation generation, and then a validation step. And one of the validation criteria can be faithfulness, or fidelity, so how well your surrogate mimics the black box. But as we started developing it in this way, we actually noticed that there are so many different parameters that you need to tune or choose, or different components to choose from, that it is way better to just validate each step as you go. Because once you do it at the end, you may get a poor result, and then you will wonder, well, with so many parameters and so many components, when did things go wrong? What happened? Whereas here you can develop each component independently, validate how it works, and then move on to the next one, being certain that whatever you're building upon has really good foundations. But in order to do all of that, we actually need to understand where surrogates come from, so how each building block contributes to the final explainer, and also how to correctly interpret the explanations. And this will be what you will be able to experiment with in the hands-on part of this tutorial. But then we should also analyze different components and choose the correct ones for our particular use case, because every single use case may require different components. And then also have some sort of tools or techniques or strategies to evaluate and validate these components as we go. Right, so with all of that, let's actually have a look at an explainer. We will begin with explainers for text data and how they work, how every single component from a surrogate works in this case, and how we generate explanations. When it comes to text data, we assume in this particular example that we have a sentence and a black box that tries to predict the sentiment of our sentence. So the first step to build a surrogate is to build our interpretable data representation. In case of text, we tokenize our sentence. So here we assign one interpretable feature, f prime, into each token in our sentence, and we indicated all of this in our interpretable data representation as a binary vector. 1 in the binary representation, interpretable binary representation, means that this particular token or word in this case is present, and 0 is absent. We can be a bit more creative with our interpretable data representations. So here, for example, we skip some stop words and punctuation in order to make the interpretable data representation more succinct. We can do even more with that in order to make sure that this corresponds into how humans reason about text by, for example, joining 2 words, 2 tokens in this representation, such as sentence and sentiment here, and all the rest remains the same. So we can use a lot of insight from research into natural language processing into generating meaningful interpretable representations for text. Then we move on to the next step, which is data sampling. Sampling from the textual domain is ill-defined in this case, so we will have to sample from the interpretable representation. This means that we'll basically draw different vectors from the 0-1 space. And like I said, this means that we basically remove some of the tokens from our sentence. Just to give you a preview of where this is headed, we are trying to assess how each token, each word in this sentence affects the black box prediction. And in order to do that, we simply remove some words and see whether this influenced the black box prediction in any way. If it did influence, it means that it's important for a particular prediction. If it didn't, it means that it's not important. So we do exactly that. Once we generate a binary sample, we recover our original representation. So we regenerate the sentences with some of the tokens removed, and we feed this through the black box and see what happens, whether it's still a positive sentiment for variations of this sentence or a negative sentiment. We can apply some more processing in the explanation generation step. And this is, for example, weighting different instances sampled from the interpretable data representation. So for example, we may want to prefer shorter edits, so fewer removals than longer edits. And we achieve that by first computing a distance between the original sentence in the interpretable data representation and some of the sampled points. And then we transform the distance into similarity with a kernel, like, for example, an exponential kernel. All of this comes together to generate the explanation. And this happens by fitting a sparse linear classifier to the binary interpretable representation and the predictions of the black box for this variation of generated sentences that you saw a moment ago. So we say that, for example, if we're explaining the positive sentiment for a sentence, we assign 1 to positive prediction and 0 to a negative prediction. We train a linear model, we extract weights from the linear model, and we use these coefficients of the linear model as our explanation. So importance of each interpretable factor. So in this case, the first interpretable component has high positive influence towards the positive sentiment prediction, followed by second token, 0th token, and third interpretable token. This may not be very informative. Fortunately, for text data, we can express the same explanation alongside the original sentence. So here you can see visualization of the same explanation for the sentence, which is way more readable because you can see that the word positive has high influence, high contribution to the positive sentiment prediction. Sentiment has also some positive contribution, sentence as well, and maybe has a small negative contribution to the prediction of positive sentiment for this sentence.
Kacper, can I just pause you there and sort of can you tell us, so for instance, positive and 0.75, what exactly does that mean?
This means that adding a word positive to this sentence moved so you could imagine possibly that you start with 0 and then adding the word positive to your sentence would move the explanation more very much to the positive side, whereas adding the word maybe would move it a bit to the negative side. So this is right. the influence of this word in this particular sentence, because the explanations are local. So the explanations are with respect to this individual sentence, and you can't really generalize this explanation beyond the sentence because they are local. So even though
Yeah. So let me just ask a question. So basically, so the word positive is present in the sentence that you're trying to explain, right?
Yes.
And so, and the 0.75 is that on what scale is that? Is that kind of like a probability? So the probability is 0.75 higher than?
This is all interpreted relative to all the other scores. It can't be interpreted in absolute values.
Right, but it is additive, right? So it's sort of positive adds 0.75, maybe detracts 0.05.
Yes, and that's because we are operating on binary vectors. So all of the features, the interpretable representation on which we train our local linear model, are zeros and ones. And then the target is also a 0 and 1, which means that the coefficients of our linear model are comparable. So imagine if you had two different features on completely different scales, and you would train your linear model on top of these, then you couldn't really compare these two coefficients of your linear model unless you normalize the features upfront. Whereas here, we are operating on binary vectors, which means that they are comparable.
Okay, thank you. And there is another question from Karen. From your point of view, what would be the role of legal professionals regarding explainability? Or is it a subject exclusively for engineers?
Well, I suppose we still have to agree on what actually constitutes an explanation when we are dealing with a black box. And you may have heard of GDPR, General Data Protection Regulation, that has come into force into EU a few years back. And in the original wording of that legislature, there was a right to explanation, but this has been scrapped from the final version that came into law. And that's because it is very difficult to actually understand what an explanation is in terms of machine learning. And I think we first have to deal with that, and what this would require collaboration between engineers and social scientists, lawyers, etc. So I think there's still a lot to discover and a lot that we still don't understand, and possibly we don't agree, especially in terms of words that we use to name things.
So in fact, the collaboration with legal scholars could be what is the definition of explainability that is actually legally meaningful? Because if you can't formalize it in law, then it doesn't really help, right?
Yeah, and then I suppose it's also context dependent. So this needs to be pinned down as well.
There's a few more questions coming in. There's a comment from Carl who suggests that maybe we should also invite anthropologists to the discussion. Absolutely, I think we should invite all the human-centric sciences and disciplines have a role to play here. Cognitive science, social science, anthropology, economists, legal scholars, and so on. There's another question from Stamatios. How does this method of finding interpretable features differ from classical feature selection with the random forest, for example?
So I suppose the objective is different, because if you generate features for a predictive model, possibly all that you care about is optimizing your predictive performance. Whereas here you don't really care that much about the final performance, but more about actual understanding. So you want this interpretable representation to actually be meaningful to humans. You want to represent something that they can relate to, or try to use something that would resemble how humans think. And if we come back to this example of explaining text, the reason why I showed you different versions of the interpretable representation is that I was getting more and more close to how humans reason when we deal with text, because if we remove a comma or a period at the end from a sentence, this doesn't mean much. Maybe it means that, it's bad interpunction or something like that, but the meaning is still the same, you would understand it. Whereas if we only focus on the important words like sentence, positive, sentiment, maybe, then we're starting to approximate how humans reason about text. You may have seen this example, and this is completely random, where you are being shown a sentence with a few of the letters or words removed, and yet you are able to you're able to fill in the gaps without knowing much more of the context. So you're showed a sentence, some things are missing, you look at it and you know what it's all about. And you may not even realize that there are some things missing because your brain is making up for the gaps. And I suppose, yeah, here we want to be as close to human reasoning and not as close to some optimal theoretical performance that we may achieve.
I think one other thing to point out in response to Stamatis' question is that really it's the difference between global and local explanations. So if you're looking at classical feature selection, you're looking at which features are globally, most correlated with the target and, contribute most to the global performance. Whereas here, typically, we are more interested in a local model. Right, no more questions. So Kacper, carry on.
Sure, thanks so much. Right, so this pretty much sums up explaining text, which was pretty straightforward, nothing tricky. Let's move on to image data. So here the setting is very similar. We have an image, a black box that decides between husky, Eskimo, and Malamute dog, and then spits out the prediction. And we want to explain it. The first step is interpretable representation. So again, we're trying to find something meaningful to humans. Images in computer science are represented as three-dimensional matrices. So it's width, height, and then RGB, red, green, blue. Communicating explanations in this format would not be very meaningful. So we are trying to find something more human-like. And you can possibly imagine that if you see a picture and there is a tail or ears, these are the sort of things that humans pay attention to. So our interpretable representation for images is dividing the image into regions, into possibly semantically meaningful regions. And here again, we split the image into parts, and one would represent a particular part being present. 0 means it being absent, and I'll get into the absent bit in a moment. Again, you can be a bit more creative about your interpretable data representation for images and try to make them as meaningful to humans as possible. So you may want to merge some of the regions, or you may even want to ask your user, your explainee, to draw boundaries on objects that would be interesting to see in the explanations. Again, sampling from the original image domain is ill-defined. So we need to sample from our interpretable data representation, which are just binary 0-1 vectors. And then when we set the value of this vector to 0, we remove part of the image, as we did with text, where we just removed words. However, removing words was possible because text natural language models do not presuppose a fixed length input, whereas for image classifiers, we need to preserve the dimensionality of our image. Therefore, the only way to remove part, not the only, but the easiest way to remove part of an image is to use an occlusion. So instead of having the original pixel values for part of the image, we replace it with a color, like for example, black, which you can see here. However, black box models can be sensitive to different colors. So just to give you an example, I used a black box, and then for this particular image used either black occlusion for all of the segments but the one with the dog's face and ears, or I used the mean color occlusion, which basically replaces each segment of an image with the mean color in that segment, and I got 2 different predictions. And this means that, well, choosing a color is actually quite important because it can provide you with different explanations. And I'll have a short demo in a moment where I'll show you this effect. We run studies on this sort of the things, so the occlusion color and also image granularity. So you saw that in the very first interpretable representation that I showed you, there were quite a few segments. And then in the following one, I merged some of them, so changed the number of segments. And actually, there are two parameters that you can tune there. So one is the actual granularity, so how many segments do you want to generate? And the second one is the color that you use for removing, so the occlusion color. And you can see that if there are only just a few segments, so here there is we have 5 segments, we split an image into 5 segments, and then we occlude either 0 of these segments, 1, 2, 3, 4, or 5, all of them. And then we see whether the black box model is still able to predict the top class of that image. So we're kind of trying to judge whether using a given color for occlusion is a good way to remove information from an image with respect to a given black box. And you can see that with a small number of segments, there's not much difference. However, when the number of segments is large, like 40, one of the methods, and the method is the mean color occlusion, diverges from the rest. And lower on the y-axis means that the black box model is able to tell the class of the image, the top class, way better than with any other occlusion method. I'll show you an example of this in a moment. But for the time being, let's come back to the explanation generation phase of our surrogate explainer. So we already saw the interpretable data representation and data sampling. Now the third step to build our surrogate is explanation generation. So again, we recover our images, and for the time being, we will just use the black occlusion from the random sample, and we feed them through the black box to see how removing parts of the image affects the predicted class of this particular data point that we are interested in. Again, we can use distance and kernel to generate similarity if we want to indicate that, for example, we prefer smaller number of segments removed, or any other way to somehow weight the samples. And then we again use the binary interpretable representation and the predictions of our black box for the sample to judge importance of each segment for a given prediction. Again, we can show it as a bar plot with importance of each interpretable feature, but to make it a bit more meaningful, we can overlay these values on top of the original image. So here for predicting husky, the face of the dog has 0.1 contribution, or I think no, the face has 88, then the bottom left has 0.1, so this part, 0.7 is the bottom right, and the top background has negative influence towards predicting husky. Right, but our problem was a multi-class problem. So how do we encode the prediction? Because the black box would output either Malamute, Husky, or Eskimo. Because we are able to explain just one class with each explanation, we need to encode it somehow for our linear model, when our surrogate linear model. And we do that by putting 1 if the black box outputs the class that we are explaining, and 0 otherwise. So you can kind of think about these sort of explanations as 1 versus the rest. So does it contribute to the husky or not husky? We do not differentiate between the other 2 classes, which in this case are Eskimo and Malamute. But what if our black box is a probabilistic multi-class classifier? Then instead of just pure predictions, we get probabilities. Arguably, we could use argmax and then follow the procedure that I outlined a moment ago, but we will be losing a lot of information. So in this case, we just, instead of using a linear classifier, we use a linear regressor and regress on the probability predictions of our black box. However, you may notice that we are losing some information. And in these 2 examples, there is a difference between the predictions assigned to the other 2 classes. So, for example, if you look at the top row highlighted in yellow, you can see that the most of the probability mass has been assigned to husky, whereas in the bottom highlighted row, it's split pretty much half and half between husky and malamute. So we would be losing quite a lot of information because here the model is not so sure about the husky prediction, whereas here in the top yellow row, it is quite sure. And we did, again, some experiments with this sort of surrogate explainers. And we figured out that using multi-output regressors, in particular trees, can be really helpful because you can number any number of classes. And if you recall ImageNet, which has about 1,000 classes, you could, for example, model 3 dog breeds out of this, and then you could generate explanations not only one versus rest, but you could also generate explanations like why is it a husky and not an Eskimo, or why is it an Eskimo and not a Malamute. So it gives you way more flexibility with the explanations that you can generate. Right, let me move on to a brief demo with image explainers. Can you see the right screen, or still my calendar?
It says surrogate explainers of image data.
Perfect. Right. So in this case, we are trying to explain a dog with a tennis ball. And the black box prediction says tennis ball 99%, and then small percentage for golden retriever and Labrador retriever. We generate a lime-like explanation for this image. And it tells us that for the prediction of a tennis ball, the segment number 13, which is the tennis ball itself, has quite positive influence, and then followed by the segment number 11, which is here to the right, then some negative influence from the background, and then again some positive influence from the dog's coat, more to the bottom left. That's pretty much okay, because the most important segment for predicting tennis ball is the part of the image that holds the tennis ball itself. But what if we try to explain any other class? So here we're trying to explain golden retriever. And you can notice that the explanation is not very informative anymore, because it only tells you, well, if you want to predict golden retriever, you just need to get rid of the ball, and then also the background in the top right gives you some positive influence towards predicting this class. Not very informative. You'd probably expect to see something of an influence from the dog itself and not the ball and the background. And why this may be. So let's experiment with different parameters of the interpretable representation for images. Here to the right, you can see an example of a data point that is used to train our surrogate explainer. If I click this a few times, you will see different examples, random examples that were used to train the explainer. We can change the occlusion color. And if you look at the left panel, you will see that once I hit explain, the explanation will actually change. And in some cases, the change is quite drastic. So this means that choosing different color, and here it's for random color, generates different explanations. So you need to make sure that you know what you're doing when choosing the occlusion color when building your surrogate explainer of image data. Another interesting aspect of this explainer is the granularity. So if I change the granularity from low to medium, so we'll get more segments here to the right, you again see that the explanation changes. And the very interesting thing about the mean color occlusion, which is actually the default option in Lime, is that as you increase the number of segments, and even if you occlude all of them, you can still kind of tell what the image shows. And this was the effect that you saw on the plot in the experiments when I told you that the only explainer, the only occlusion color that differs for a high number of segments is the mean color occlusion. And that's mostly because of the mosaic effect that you can see. So if you have a lot of segments that you split your image into, they will have more uniform color distribution within themselves, which means that even if you occlude them with the mean color, they will still pretty much convey what the original pixels conveyed. So you should avoid high number of segments with the mean occlusion color. And the rest of the parameters also matter.
Kacper, can I pause you there? I have a question, and there's also a question in the chat. So my question goes again back to the numbers here. So previously, when I asked about the number, we were in binary classification, okay? And then you learn a local model, which is a linear classifier, and basically the coefficients of the linear classifier give you that bar chart, basically, and a positive and a negative influence, right? Here, you've moved to a multi-class scenarios, and now we are doing linear regression.
Yes.
So what do those numbers mean?
So again, you could interpret this as, so we fit the linear model with an intercept. So you could interpret the intercept of the linear model as the kind of average prediction for this sort of an image, and then presence and absence of each of these segments moves you a bit to the left or a bit to the right on that scale. So if we include the segment number 13, this would move our probabilistic prediction of the tennis ball 0.13 less. So it would decrease the probabilistic prediction of our black box if some segment number 13 is present, whereas adding segment number 23, which is this part of the ball, would increase the probabilistic prediction of the tennis ball. So here we explain each class individually. So for example, if I change to golden retriever, then we train our surrogate on the probabilistic predictions for golden retriever for our random sample.
Okay, but then I have a follow-on question, because in the binary classification example, we could see that the coefficient was either positive or negative, and that gave me, you know, whether the bar was green or red. So where does the green or red come from here? Because it doesn't come from the numbers.
No, so the coefficient itself can be negative or positive in the surrogate linear model.
Right, so should it then be minus 0?
So these are absolute. Yeah, go on.
So should one of the 0.07 be minus and the other one plus?
Yes, so the number is absolute, and then just the color indicates whether it's negative or positive. So whether it's a minus or a plus.
I see. So here you rank them on absolute value.
Yes, because we are interested in importance, in the magnitude. Is it a big contribution or small contribution? And then the secondary criterion is it a positive contribution? Is it a negative contribution?
Right. Okay. There's a question from Damiano, which I'll read part of it, but maybe, Kacper, you could also look in the chat. So once we have an explanation for the black box model, what is the point in still using the original black box model? We can use the explanation for the task instead of the black box model, since we know how it works. Or did I miss something? And then there's a second question.
These are local explanations. And for example, in case of text data, they are only valid for the sentence that we are explaining. And for image data, so you need to generate a separate linear surrogate for each individual image, which means that you can't really generalize them beyond these instances.
Mm-hmm. But there has been also research by Rich Caruana, for example, by training a global surrogate model, let's say training first a deep neural network and then train a shallow neural network on the predictions of the deep one, not on the original data. And then you basically have a surrogate model that in some sense replaces the deep model. Is that right?
Yeah, you could possibly do that, in which case you're just simplifying your model. But then the question is, you can obviously use the second simpler neural network for predicting your data, but can you really use it for explaining anything? Is it just trying to simplify the model, or what was the objective here? Because I don't think that the simpler neural network is any more explainable than the more complex one.
Well, I mean, if it didn't have hidden layers, then it was a linear model itself, and and hence explainable because you use a linear model. But I see your point. I think the difference is that in one case we're explaining predictions, and in the other case we're interpreting the model as a whole. And I think there's a difference there. There's another question. For image data, the model learns structure based on each pixel. How do we know the segmentation for interpretation is really meaningful for the model? I think that's a good question. So clearly this depends on the segmentation. So how can we make sure that we have a good segmentation?
So I think so when you build the segmentation, it's not as much whether it's meaningful for the model, it's more whether it's meaningful for the human. I suppose small differences in segmentation can result in disparate explanations, and that's definitely something that we should look into. But again, in case of generating the interpretable representations, what we want is something that is meaningful to humans. So here, in case of this particular image, it would make sense to create one segment for the ball, just because it's an entity. It's something that we would use in reasoning. And then for the dog, maybe ears separate, muzzle separate, the body of the dog separate. There are some papers that instead of using occlusion for removing parts of images, cover part of image with another object just to see what happens. So for example, you would cover the tennis ball with, I don't know, a cricket ball or something else to see whether this would affect the prediction in any way. So there are different ways to do that. But all in all,
okay. Yeah, go ahead.
All in all, it has to be meaningful to humans because you are directing these explanations toward humans.
Yeah, so I guess the question points us towards that what you call the interpretable representation plays a crucial role. And I think another thing, you will get onto tabular data in a moment, but the other thing is that this is very different for images, for natural language, and for tabular data. It's actually the most easy in natural language because you can just remove words and see what happens. It's a bit harder for images, as you've just talked about, and it's actually not that straightforward for tabular data at all, but you will come on to that, right?
Yeah.
Okay, carry on.
Right, so let's continue. And the next step is looking into surrogate explainers for tabular data, which is the most difficult case of all: image, language, natural language, and tabular. So again, our setting is in this case just a two-dimensional data and a data point in that space. So here we were trying to explain 0.2, 0.8, the green star, which is being classified by a black box as either red or gray. Again, we start with interpretable data representation. So you could imagine just using the exact feature values, 0.2 and 0.8, but this is not quite how humans reason about numbers. A more natural way would be to go with, for example, ranges. So you would be interested, instead of 0.2, in, well, is it between 0.0 and say 0.4? You want to generalize it as much as possible And a good intuition for that is, for example, if you then would name these regions in which you would split into low, medium, and high, for example. So we want to abstract away the numbers in order to convey the explanation. And the first step in order to do that would be to discretize your data. So here we split our data into quartiles, and you can see that each axis, so each feature, X and Y, is split into 4 parts. But this only gives us discrete representation. And for all of the other cases, we had a binary representation. We switched something on or off. So we're not quite there yet. So the second stage of the interpretable data representation for tabular data is then binarizing our discrete representation. So this provides us with 2 binary features for each axis and 4 different regions. So 1 in our binary representation would mean that we are in the region of the explained instance. So in the blue region here, this means this is the split on the x-axis where our explained instance is. And all of the other 3 of the discrete bins are 0 because we are not there. We can only have 2 values, 0 and 1 for each feature. And the same applies to the y-axis. So if we are in the top row, we are in the 1 region of the binary interpretable representation here, and 0 otherwise. So this gives you 4 regions in case of 2-dimensional data. 1, 1 is the hyperrectangle where our explained instance is. 0, 1 is the same region on the y-axis. Same on the y-axis, but different on the x-axis. This is the same on x, but different on y. And this is different on both x and y when you split. So this gives us the interpretable binary representation for our tabular data. However, when you go down this road, there are quite a few obstacles. And one of them is the curse of dimensionality. So once you start splitting, you get an exponential growth in instances, which means that in order to discover these regions, you would have to get quite a lot of data in the neighborhood to understand it. So here, because we split each feature into 4 regions and we have 2 features, we end up with 16 discrete hyperrectangles. And then we reduce it a bit, fortunately, with the binary representation just into 4. But you can imagine that, for example, with 11 numerical features that we need to split into 4 regions, you would end up with more than 4 million hyperrectangles. And then even after reducing it, you would still have 2,000 unique binary encodings. And then you need to sample data and somehow try to make sense of all of that. So this becomes quite difficult. What you try to achieve with your both discretization and binarization is trying to approximate the black box decision boundary, because in the end, you are trying to kind of figure out how the black box decision boundary goes in the neighborhood of the explained instance. So if the explained instance is the green star here, you want to figure out how the black box decision boundary would run. And for this data set, it would go across here and up there. And here, for both the binarization and the discrete representation, you can actually visually inspect and see, well, okay, it actually kind of splits the decision boundary quite nicely, so we're good. But what would you do in higher dimensions? You can't really inspect it visually anymore. So the way to go is to assess purity of each region. And by purity, I mean, are all the instances in each region mostly red or mostly gray? You want to avoid the regions where you have, say, half and half, red and gray, because this means that the black box decision boundary runs across this hyperrectangle, so you're not really approximating it very well. But in this case, this looks very reasonable. How would you do that in higher dimensions, where you just compute either Gini index or gene impurity for crisp classification, or mean squared error for probabilistic classification. And you'd calculate that based on the predictions of your black box for each individual hyperrectangle here or here. And this kind of allows you to assess whether you do not cut through the black box decision boundary with your discretization or binarization. So it's a really good proxy. Having said that, if you think about other models in machine learning that use this sort of optimization criterion, you'd come across decision trees. So then instead of actually doing manually discretization and binarization, you can skip these two steps and use decision trees to split your region into parts. And here I restricted the number of leaves in the tree to 4, just because we ended up with 4 different representations with the previous 2 steps. And then you can also encode them in a binary way, like so. So this would be all of the interpretable representation generation, quite a lot to take in, but this just means that there is a lot of parameters to tune there, and you have to be very careful when building interpretable representations for tabular data, and your main criterion should be purity of your splits. Next, we move on to data sampling. So even before we start, we need to decide in which region we will be sampling the data. So you can either sample in the original domain. So you can see that to the right, just from these 2 features. You could possibly sample from the discrete representation, or you could sample from the binary representation. Each one would give you a different result. So how would that work? Well, for binary, you can only sample from two different values on each feature. And all you would get is, well, if you sample 1, 1, you would know that it's somewhere in this region, blue and yellow. If you would sample 0, 0, this would mean that it's somewhere in the region without any color. And 0, 1 would, for example, mean that it's somewhere in only yellow region. Sampling in the discrete would be the same, but you would get more granularity. So you'd know the exact hyperrectangle where your point is, but you would still not know the precise values of features in the original domain. And this becomes a bit problematic if you sample from either binary or discrete, because if you recall, we need to recover data points in the original domain in order to predict them with the black box to see how it behaves in different parts of our decision space. And if you sample in either binary or discrete, you don't get that. So the best you can do is to actually then sample from one of these hyperrectangles. And this, unfortunately, introduces a lot more randomness into our explanations, which is not really helpful when we're trying to explain something. And this is an example of how you do it if you sample from the discrete representation. So you can see that, first of all, we get a global sample of our data. And second of all, every time you run this algorithm, you'd get a different sample. Therefore, you may get a different explanation. If you sample from the original domain, which is the preferred way in this case, again, you may run into some problems. So if you just use a naive sampling, like, for example, using Gaussian, you may not discover the decision boundary. So you can see that only most of the points here are blue and only 4 or 5 are red. This means that you haven't discovered the decision boundary, so there's nothing that you can approximate. This sampling is only based on the density of the data. You can also use the predicted class of your sample to somehow guide the discovery. And these are 2 methods that do so. And here you can see that you actually discover the black box decision boundary. So blue is the explained instance here. So you have something to approximate. Again, how do you know whether a sample is good or bad? In case of the interpretable representation, we try to make the splits as pure as possible. Here you want to go the complete opposite direction. You want to have as diverse sample as possible. You want to collect many different points from different classes. So assign different classes by the black box, because you want to discover the decision boundary of the black box, because ideally, this is what you want to mimic with your surrogate. And again, you could use the same two metrics, but you would try to optimize them on the other end of the spectrum. So you want to have as diverse sample as possible. Finally, for the explanation generation, again, you can do distancing and weighting. And the question is, which domain do you calculate these metrics in? You can see that based on different domain in which you do that, you get sort of different results. And if you combine that with the similarity metric, so kernelization of your distance metric, this becomes even more complicated. And how do you decide? Well, this is, again, problem dependent. With images and text, you could convey the explanation with the original instance. So you could just overlay the explanation on top of the image or the sentence, which was way easier for the explainee to understand and read. In case of tabular data, this may be a bit overwhelming as well, because if you have a lot of features, you do not really want to communicate all of them to the explainee. So you may need to resort to some sort of feature selection method and select the top 4, top 5, just not to overwhelm the explainee. And the reason is that, again, you can only convey an explanation, a surrogate explanation of tabular data as a bar plot. This is an example of a surrogate explanation for tabular data. And you can see that we use the regions, so the splits that we generated originally, and we try to convey whether being in this region on both the x-axis and the y-axis independently has positive or negative influence for predicting red class. So for example, for the green instance here, being in the region between, on the x-axis, between 0.31 and 0.47, so here, has negative influence on predicting red class. Whereas being on the y-axis between 0.54 and 0.67 has positive influence on predicting the red class. So being here, other than in the pure blue region, is beneficial for predicting red class, whereas the same for the x-axis has negative influence. And this may be a bit counterintuitive, but I'll show you an example in a moment, and hopefully this will make more sense. Right, so let's move on to the demo for tabular data. So here in this demo, we are trying to classify the iris flowers, so the very famous iris dataset in machine learning, where we have 4 measurements: sepal and petal length and width, and we are trying to decide whether it's a versicolor, setosa, or virginica type variety of the flower. So again, we are splitting our tabular data into regions, and then we are generating a surrogate explanation based on these regions. So now, just to show you how it works, if you think a bit from what would happen if I move the split on the x-axis from 3, say, to 6, do you think the explanation would change? And the answer is no. What about if I, for example, move the split on the y-axis from 1 to 1.5? Do you think that the explanation would change? Again, no. So what if I move the one from 0.5 a bit higher? And the explanation changes. And the reason is that mostly what matters is the prediction of the points and their quantity in each region. And if you recall, the only regions that matter in the end are the blue only, yellow only, and blue and yellow. So if I move any of the other splits, they do not really affect the actual interpretable representation. So moving any of the other splits does not really have any effect on the explanation, whereas moving the ones that matter would change the explanation. Also, an interesting point is moving the one from 2 to 3, because the inclusion of points in these regions wouldn't change. So the explanation wouldn't change as well, because we haven't covered any more points or any points of other class.
Kacper, can I pause you there? So the first one, so if you, I don't know if it's easy for you to put everything back, but roughly where, yeah, that one was at 2 and the other one was at 0.5, I think. Okay, yeah, let's leave it here. So my question to you is, clearly X and Y are highly correlated here. So yet we see a big difference in the length of the bar for petal length and petal width. Is that to do with the fact that length is on a different scale than width?
No, that's because our surrogate is a linear model, and linear models assume feature independence. And if you go a bit deeper into trying to understand what happens is, so petal length in this region has quite positive influence. And that's because being outside of this region, we don't see any points. So being here is very indicative of the red class. And then again, because of the feature independence assumption in our linear local surrogate, the same happens for the y-axis. However, if you just operate on the x-axis, so you forget about any y-splits, you can see that you can easily separate the red cloud with just a split on x. That's why it has way higher influence than y, because with y-axis, it's a bit harder to separate the clouds, but it has to do a lot with the assumption of feature independence, which is here not true.
So you are saying that suppose that I would multiply the petal width by 2, so that basically roughly the two scales are the same, that wouldn't change the figure on the right?
No, it should not.
So what you're saying there is that these these explanatory plots are scale independent. Is that right?
Yes, because in the end, what matters is the quantity and the black box prediction in each of the meaningful regions. So then the meaningful regions are blue only, blue and yellow, and no color.
Yeah, okay. There's a question from Patricia Pereira. So she asks about relation to attention mechanisms from deep learning. So in the case of text and images, what are the key similarities and differences of surrogates compared to attention mechanisms? And could one relate surrogates for tabular data also with attention mechanisms?
I'm not very familiar with the attention mechanism, so I'm afraid I can't really answer that.
Okay, so maybe that's something that could be discussed offline. But thank you for the question, Patricia. All right, let's carry on.
Okay, so that's most of surrogate explainability. And just to give you a bit more technical details on why and what matters in terms of surrogate explainers. As I said earlier, so just to clarify, here is just a fictional depiction of tabular data split into 3 regions on each axis. We are explaining the region with the star. So again, this would be encoded as 1, 1. Green would be encoded as 1, 0, blue 0, 1, and red 0, 0. And the equation to the right is the analytical solution to ordinary least squares for 2 dimensions in terms of using the binary interpretable representation and the average prediction in each of these regions. The red part in the equation relates to ordinary least squares when you fit. So let's start with blue because blue is more important. Blue is important when you fit ordinary least squares, so your surrogate with just without intercept, whereas blue and red matters when you fit your ordinary least squares surrogate with intercept. So the easiest case would be without intercept. So we are looking at blue only part of the equation. And what it tells us is that all that matters for the coefficients of our surrogate, therefore the parameters of our explanation, are quantities of points sampled in each region. So W11 is the number of points that you sample in the explained region, so yellow. W10 is the number of points that you sample in the green region. And W01 would be the number of points that you sample in the blue only region. And then the Y bar would be the average prediction in regions both 1, 1 and 1, 0, so in the entire row here. And 1, 1, 0, 1 would be in the entire column. No, the opposite way. So 1, 1, 1, 0 would be the entire column, and 1, 1, 0, 1 would be the entire row. So what's the average prediction in this row? And based on that, you pretty much now have all of the technical details needed to interpret this short demo that I showed you a moment ago, why some of the some moving around of the interpretable representation mattered and other moves did not matter at all, because it all has to do with the number of points that you sample in the explained region and the entire row and column of the explained instance, as well as the average prediction in these regions. And this will be helpful for the hands-on that we'll get to in a moment. So just to conclude, before we break for a bit and then start the hands-on exercise, the key takeaways from this talk is that having an explanation is not enough. You should trust your explainer, and it should be trustworthy. And in terms of surrogates, they should be made tailor-made. They should be configured for the application at hand. You can't just get a random bunch of components for your surrogate explainer and then apply it to any problem. And for example, if you think about the difference between the image surrogate and the tabular surrogate, for the interpretable representation in particular, having the same sort of segmentation. So if you imagine just segmenting an image and then sliding the image, different image, and reusing the same segmentation, it would not matter. It would not be very informative, because if you have one segmentation, say you just make a grid and use different images, you wouldn't capture important objects in that image. And the same is true for tabular data. So for example, splitting your data into a grid is not very informative or very helpful, because different data would require different interpretable representations to convey different meanings. And this is context dependent. What does that feature mean? How does it change? So you should build each component of a surrogate for the problem that you are facing. And this clearly highlights that these are not monolithic entities. They are quite modular, and you should pay attention to every single module that you put into your surrogate. And finally, these are only diagnostic tools, and they become explainer only when you understand the properties of the method that you use and the outputs that it produces. So in the end, I'm sorry to disappoint you, but there is no magic formula for building surrogates. You actually need to understand every component that you use, and you need to understand the problem that you're facing and that you're trying to explain, and some characteristics possibly of the black box that you are trying to explain. If you want to learn more, there is this open source software package that we are developing called Fat Forensics, and it has been used for some of the demos that I showed you today, and also the hands-on that we'll do in a moment. We had run a tutorial covering this topic more in depth at ECML PKDD last year, and all of the resources from this tutorial are available. We will publish a self-paced online learning materials on machine learning explainability in the coming months. And also, yeah, this is the summer school. So, and if you're here, great, you have just learned some more about explainability with surrogates. We'll break for a moment, but first let me show you some of the resources that we prepared for the ECML PKDD tutorial last year, which go more in detail with building surrogates. So if you navigate to events.fatforensics.org, you can find all these Jupyter notebooks there, and they go step by step computationally with all of the issues that I covered today for tabular data. So you will see different ways of sampling your data, and then different ways of measuring these samples, whether they are good or bad, some discussion about that, both with quartile discretization, decision tree discretization, and different metrics for that. Also, some materials on sampling in the neighborhood for both two-dimensional examples, just for the purposes of visualization, for a few data points, as well as for higher dimensions, but then all you get is just a bunch of numbers that indicate purity of each segment and the diversity of your sample. And the final notebook from this bunch of resources shows you how to build different sort of surrogates, including line-like explainers and rule-fit-like explainers from the same bunch of components. So if you're interested in the more computational aspect and hands-on aspect of this sort of thing, I encourage you to have a look at it. Yeah, and I think we'll break for 5 minutes, so until 5:45, and then we'll come back to a hands-on Jupyter notebook for which you don't really need any coding. This will be a widget that you can play with, something like that. So yeah,
Kacper,
yeah,
could you maybe just point people towards that
good point.
notebook, so and then we break so that people have time.
That's a great point. So this is the URL where you can access the notebook, and I'll leave the screen on.
Okay, so there is another comment from Patricia. But this explanation is for sequence-to-sequence attention mechanism. Attention mechanism can also be applied to sentiment analysis. Let me know if you look into this and possible answer to my question. Okay, so sure. Patricia has given her email address there. Okay, so the suggestion is to people, if you, so after the break, a short break, 5 minutes or so, we will come back to the hands-on aspect. And so open the Colab notebook, and then you can, then Kacper will set you a small assignment with some explanation, and that will be the last part of the tutorial. And we hope to finish on time, which is 6 o'clock continental, right?
Yeah.
Okay, good.
Right, I think we can resume. So I hope everybody got access to the notebook. Let me just share my screen and show you how to use it. So first of all, once you open the notebook, you need to connect. I hope you can see the notebook, right? So you will have a connect button here in the top right, and then all you need to do is click runtime and restart and run all. And towards the bottom, you should get a widget that looks just like that. For your help, there is the formula and the example, the toy example image there as well. But let me get back to the widget, which is the important bit. The first set of parameters that you have in the notebook is length and width, and this allows you to change the instance that you're explaining. So the yellow star here, if I just move width a bit up, so for example to 0.5, you will see the point moving up to 0.5. So this allows you to control the instance that you're explaining. Next is the explained class. So you can explain this star instance as either the red class, so Setosa, versicolor, yellow, or virginica, blue. Then you can control the number of samples in each hyperrectangle. So if I change, and this corresponds one-to-one with the location of hyperrectangles in this image. So what this 100 is here, then this 100 is here, this 100 is here, etc. So for example, if I change this to 1, you will see that the top left gets only 1 point now sampled. And it's here, if you can notice it. And then finally, you can move around the discretization. You'll see this one moving from 5 to 6. You get one more choice, whether you want to model interset or not. I suggest you do not model interset, just because then trying to play with the formula and the actual explanation is a bit easier. Since there are two important factors in generating surrogate explanations for tabular data, one is the ability of your interpretable representation to approximate the black box decision boundary, and the black box decision boundary is the shading in the background. And the other one is the number of samples. You can use two black box models. So one is a decision tree, and it is only used because it has axis parallel splits. So it's a bit easier for you to align your splits, your interpretable representation splits with the black box decision boundary. The other one is a logistic regression because it's not axis parallel. So it's a bit more tricky to align your splits with it, but also it allows you to get a bit of diversity in your black box predictions. Because remember that the two important factors are the number of instances in each hyperrectangle and also the average prediction. So if you move around your partition such that it covers a black box decision boundary on angle, you will get a different average prediction in that region, which will affect the explanation. So the idea here is to play around with your discretization, so the two splits on X and Y, as well as the number of instances, to try and get as disparate explanations as possible, which should give you some sort of intuition, first of all, how surrogate explainers for tabular data work, but also should convince you that you can manipulate the explanation so that you get whatever you want out of it. There are obviously some restrictions because of the average prediction that comes into play when computing the factors of your explanation, but this can be used to do fair washing. So fair washing is a concept where you would use your explanation to convince your audience that the black box model is fair, where in reality it's not fair. And as you play with this example, you will see that you can actually sometimes make some of the explanation coefficients 0 or positive instead of negative just by changing these parameters, which would possibly allow you to hide unfairness in your black box with a technically valid explanation, yet manipulated such that it disguises some of the undesired properties of your black box. So I'll give you a moment to play with that. And then I'll show you one or two examples and we'll close the session. So have a go at the widget. If something does not work for you, just message in the Teams chat and I'll try to help you debug it. Okay, so just to close the session, let me show you two interesting things that you can do with the notebook. So if you do not model the interset and for the logistic regression, one is that we can get rid of the off-diagonal points, so the ones with 0, 0 in the interpretable representation, because they do not matter for the explanation. So if I just zero out all of these samples here, you will notice that the explanation does not change because these do not contribute anything. And the other one is that moving the split, the first split on the x-axis, you can actually change the magnitude quite a bit. So if I move the first one a bit to the left, you can see that the third petal width has lower negative importance and petal length has higher negative importance. And if I move this the other way around, you can flip the magnitude. And this is because of the average prediction. In one case, we are very true to the black box and we only have red points in the region, whereas here we start including orange points as well. And if we go further, this will start increasing even more, which means that you can manipulate the explanations quite easily just by not aligning your interpretable representation with the actual black box decision boundary. You can also find a lot of other interesting effects here, so I encourage you to play a bit more with that. And that pretty much concludes this session.
Thank you so much, Kacper. And people are asking if you could please share the presentation in the chat, so maybe then they can, have a look.
Sure, but it would be just easier for me to generate PDFs, upload them somewhere, and share the link with you, and then you could possibly distribute the link.
Of course, of course.
But yeah, in the meantime, if you want to have look at the slides, there is a bit older version of this deck of slides on our website. So if you head to events. I'll type it in. So I'll type in the link to the old slides in the chat, and we'll upload the new version soon enough.
Thank you.
Just give me
I think that's my suggestion would be, because you have an events.fatforensics.org.
Yeah, a new
so
event
if
there.
you make a new event page for this,
yeah, I will.
And then post it there, and then all the
Sure.
materials are there, and then Martina can just post a link there to everything. There was a question by Carl. Is there a way to query the model for counterfactual examples of a given data point or prediction?
Well, you could possibly just play around with feature, not in this widget, but you can possibly query just the black box for it with different feature values and get a prediction. However, if we are talking specifically about surrogates, it is not possible if you use a linear surrogate. But if you use a decision tree as your surrogate, you could do that. And one of the papers that discovers and analyzes such a scenario is Lime Tree. It was referenced in one of the slides where we fit a surrogate decision tree, and then we can ask questions. How can we make the image predicted as a husky into a Malamute? And this would be, oh, you just need to switch off this particular part of the image, so just cover it with black. And you could do similar reasoning for tabular data by moving it into different regions in your interpretable data representation, or for text by removing tokens.
Okay, are there any last questions or comments? Okay, so Kacper has just posted the link to an older and also more extensive set of slides, but in that same Fat Forensics website, there will be, oh, actually you have fatforensics.org, don't you?
Yes, but that's for the package. So the events page is here, and we will put a new sub page there for the materials from this summer school.
Okay. Excellent. Well, if there are no further questions or comments, we've come to the end. So thanks everybody for listening and sticking with us. Thanks for your questions. Thanks very much for Kacper for the presentation. Thanks to Martina for organizing this and giving us the opportunity. And just to remind everybody, there is a second day of exciting tutorials. Martina, can you remind us of the program?
Yeah, tomorrow we will have, I can share if you want the the slide with the, so doesn't not run so smoothly when you have to share your screen, you know. Okay, maybe now I can. Okay. So you can see the day one now. It's what we have done today. And this is the day two. Tomorrow, the focus will be on the approaches to learning optimization and reasoning. As also Professor Michela Milano said at the beginning of the day one today. And tomorrow we will have Luc de Ret and his colleagues talking about some insight from their AI to neurosymbolic AI, so integrating some paradigms. And then we will have Andrea Orlandini that will talk about automated planning and scheduling, about development of robust and dependable systems. And then we have our, closure with Neil York-Smith, that we will have a talk about agent-based modeling for social simulation. And then we will have our conclusion.
Excellent. So thanks very much, and I look forward to tomorrow. Okay.
Thank you so much. Love you. Bye.